add email address for the participants of the semester who wants to be in the mailing list. So there is a mailing list about activities of the semester, seminars on Tuesday, Thursday, and so on. So if you're not on this mailing list, you can write to Annette, and she will make you into the mailing list. Correct. We'll put Annette's email on the board, maybe? Is it good?
On the corner right. Sorry.
Great. And now we are going to end the second lecture on acylindricity of the Cremona group.
Okay, thanks. Okay, so as I told in my first lecture, so the aim of that will be tomorrow will be to find the WPG element in the Cremona group. So first of all, we need a space to act on, and this is my goal today, is to make you understand what this space looks like and what is the action on this space. So first, so action no VP2. So in fact, the space we will build is an analog of the hyperbolic model for the hyperbolic plane, which is X. So these are R3 that satisfies this bilinear form. And okay, if you do this, then you have two hyperboloid, you have one down, and so you can ask that X is positive, and you get this thing. So I want to build exactly the same, but instead of being in R3, I want to be in R infinity. And if my field is, so if we take C, if my field is not countable, in fact, this will be not with a countable basis. Okay. So my aim is this thing, is to build such a space on which the Cremona group acts. And so first of all, okay, I need to build an ambient space. That will be my R infinity. And also I need to build a bilinear form on it. Okay. So so it will be in a few steps, but so please, I know that most of you are not familiar with hyperbolic with birational geometry. So if you have any question, please ask me. So my goal of today is just to build this space. So okay, if you have question, don't well, feel free to ask. So first of all, we'll define what is a divisor. Okay, so okay. I consider S a surface, which will be projective, smooth or regular, so a nice one, okay? And so you can have, okay, you can have in mind P2, okay? You can just think P2. And so a divisor D on S, so S will be always a surface, like this, I don't have to write it all the time. This is just a formal sum. This, so with coefficients. So these are irreducible curves. So CI, they are irreducible curves on S. The I will be belonging to Z. So there will be the coefficient. So it will be kind of thinking to the multiplicity of my curve. And we want this sum to be finite. Just a finite sum with some coefficient of curves. And yeah, sorry, okay. So yeah, and this what I meant is that it's so if you take a polynomial, yeah, and you take the zero set of a polynomial. So this is it. Okay, so now okay, now I will start to have a bilinear, well, I will speak about the bilinear form that we want to study. So our space will be not divisor, but someone that I will explain later. So in fact, as I explained, well, as I just mentioned vaguely before, well, if you have two irreducible curves, you can intersect them, and you can try to give a good definition of this. There is all a theory on this, so I will not spend all my time on it, but just to give you a bit the idea. So if you have two curves, so let's C1, C2, two irreducible curves. So as Piotr says, so this is the zero set of a polynomial. This is the zero set of another polynomial, okay, locally, let's say. And you can, okay, so you can define their intersection. And the point is that, for instance, okay, if the intersection is transverse, okay, it's easy to count even if it does something like this, okay. Now you have two intersection points and it's clear. But you also, you want to have a way to move the divisor. So you don't want that this intersection number is different from this one, okay? So here, of course, you have one, but if you move just a bit more, in fact, well, this one is as multiplicity 2. Okay, so this is a reasonable thing we want to do. And so what you can speak about is that so the local intersection to a point, so you can define the local intersection at a point P. You can define it to be the C1 intersected with C2 at P. So the way to do it is to do the complex dimension of the ring of regular function at P. Okay, I will explain. Quotiented by the ideal generated by the two equations. So what we mean by this, these are quotient of polynomials such that the denominator doesn't vanish at P. Okay, so if I do just a first example, so for instance, if I take what I did, so if F1 is so okay, F1 is a polynomial y, so yeah, and if F2 is a polynomial x2 minus y, okay. So in fact, okay, if you do it well, this thing, if you do it in the good way. And so we want to compute this thing. So we want to understand what does it mean, this thing. So here I said that, so P, these are the quotient of polynomial such that so, G1, G2 polynomial, such that V2, so I want to do it locally in 0, 0. So this will be my point P. And you want that G2 of 0, 0, it doesn't vanish like this. Okay. So we want to compute this dimension. So we have P quotiented by F1 and F2. And because the denominator doesn't vanish in 0, you can see this. So you can put a 1 plus something. So you can see this as a formal. So the formal sum of coefficient of so you take infinite. You don't take polynomial, but you go until infinity. So this is the I forgot the name in English. Yes, sorry. So thank you. Power series of x and y divided by the fact that you want that by the ideal generated by y and x squared minus y. So this means that each time you have okay, you killed all the power of y bigger than 2, well, at least equal or bigger than 2, and each time you have x squared, it's like a y. Okay, so then, okay, if someone can tell me what we get. So this will be generated by y, but by what? Sorry? Yeah. And so, and this is dimension 2. And this is exactly what we wanted here. Okay. And okay, and now, okay, I said that my people, they are linear sums of divisors, so you just do the same. So if you want to define the intersection, you do the same, but you sum to, well, you do the local intersection, but you sum them. So by linearity of the divisors, you just by linearity for divisors with no common components, you get a intersection form on divisors. But this is not really satisfying because as we see, oh yeah. So then, no. What I meant is that here this is a sum of. So okay, first of all, if you have two curves, so you look at all the intersection points and you compute, you sum all the. So okay, let's say. So the intersection C1 and C2, sorry, this will be the sum for P belonging to C1 and C2 of this local dimension. Wait, I forget to state, sorry. So this will be the number of intersections between curves. Okay. This is yes, thank you. I went fast. And now I want to do intersection with divisors. So now what I do is that I have two divisors. So I multiply. So I will write it down. It's better. Sorry? Yeah, this I will do it after. Yeah, then I will explain how we move here. So then you do D1 intersected with D2. So this is the formal sum of Ci. This is the formal sum of Fi. And now what I do, I say that the intersection form is the intersection form of G. This is the sum of AI BG of Ci. This is what I meant by linearity. Yeah, exactly. Yeah, sorry. Okay, but in fact, okay, this is but we want a way to move the divisors, like I said, and this is fixed. And okay, this I will not really explain, but yeah. So here we have almost what we want, but the problem is that it can be that they have a common component and we don't know how to deal. And there is a nice way to move the divisor. We can, well, if you want, we can do it in the tomorrow, but it's not mandatory. And so we will say that we can move it in this family in order that they don't have any more component. So there is a way to do it. There is no component. So in fact, there is something which is called linear equivalence that allows you to move divisor such that the intersection is preserved if it's well defined, and if it was not well defined, this will be the definition of your intersection. Okay. So okay, so then you get really intersection form on divisor.
So when is it not all the time? They have a common component, or?
Yeah, exactly. So even if they have a common component, so in fact, what you want to do, so if you have a line, you can do the self-intersection of the line, and you can just say that, okay, if you move a bit the line, it will be like this, and then you have self-intersection one.
You just declare it to be one, or is there some?
No, okay, I didn't, but in fact, if the definition of this is that you have the two, they are linearly equivalent if this divisor minus this one is, so if there exists a rational function, so it's a function which goes from the surface to P1, so it's that the zero set of this function minus the pole set is equals to this difference. Okay, so okay, we can speak about in the exercise. But, so for instance, in P2, which is nice, but which is not the case of every surface, this equivalence tells you that any curves of any degree will be linearly equivalent to the line times the degree of the curve. But this is something really specific to P2. Okay. But so now what I will be really more interested in is that if I take the Néron-Severi group of a surface, which will be the group of divisors. So okay, this they form a group with a plus, with a formal plus. Okay, so this is a group of divisors, and we can put equivalence on them by saying that D is numerically equivalent. Numerically equivalent to D prime. Okay, to divisor if and only if you take any irreducible curve on S, then the intersection number between D and C is the same as the intersection between D prime and C. Okay, so this is the equivalence I want to have on my set of my group of divisor. And now, so let's do an example. Yeah. Yeah, I didn't. Yeah, I'm messing with my. Yeah, so sorry. This should be a point. Yeah, I'm sorry. Thank you very much for the. This will be my thing, and yeah. Thank you very much. Okay, if I start to, yeah, okay, yeah, thanks. Other question? It's okay. So, for instance, if you look at the Néron-Severi group of P2, with exactly what you asked me before, what is this group? Exactly. So this will be Z. So this will be generated by the line. Because we said that any, well, I just comment, so I just said it like this, but this is because for every curve of degree D, okay, you know that it intersects the line in D points, okay? So then you know that, yeah, so D times the line, it's supposed to be, so C times the line, this is D. Okay, so this tells you that, in fact, C is numerically equivalent to D times the line, C as a divisor. Okay, so this is generated by the line, okay? And, okay, if you intersect the line by, if you do the self-intersection, that's okay. This is one, okay? You intersect two lines and, yeah, 1 point. Okay, now, what happens if I blow up a point? Okay, we have already seen, so we have P2, okay, we have our line, and we blow up a point P that was not passing through L, okay? So then, on the surface up, so SP, let's say. So here we have something which is called exceptional divisor. And here we have the line that doesn't intersect EP. So this is still of self-intersection 1. And as I just stated this morning, this is of self-intersection -1. Okay, but now I could also blow up another point, which is distinct and still not on the line. And we get an exceptional divisor. So we call it exceptional because it's alone is in its equivalence class. That's why it's called. UQ is -1. And so now you should start to see a form that appears, which is of signature 1, -2, and I can keep going with this thing. So if I stay here I have a, so okay, if I go here, what is the Néron-Sévigny group of this surface? This is generated by the line, but these two, they are alone in their own class. So the Néron-Sévigny group is generated by L, EP, and EQ. So if instead of staying in Z, I want to transfer these things by R, then I get R3. And I have a base where this one is of self-intersection 1, this -1, this -1. So I start to have a, so the intersection form is of signature. So, okay, so now I can have a hyperbolic space inside. Okay, here I have the hyperbolic plane inside. But we don't want to do just this. So what we want to do is that we want to blow up all the points at the same time. Okay, so a bit like in the talk of Sebastian. So we don't want to just remove a set of points of puncture, but also we take an inductive limit. Okay, so now, take inductive limit. So take Z of P2 or S is the same. It will be the inductive limit of the Néron-Sévigny group of surface S prime such that S prime is obtaining. So this is a morphism, and we said that this means that S prime is obtained by S by blowing up a finite amount of points. So this is blowing up. So, okay, if I want to see this a bit more with the basis, I can, I'm sorry, I transfer by. So this set, in fact, these are the formal sum. So element of this set, there will be some, so it will be a coefficient. So, okay, let's suppose I do Z of P2. This it will be some coefficient in front of the class of the line, plus some coefficient in front of the some points that I blow up, where this sum is finite, and so lambda E, lambda. If I am on the field, it belongs to the field. And okay, what I do here is I do just in the algebraically closed field. Okay, and just a remark I wanted to do, and yeah, okay, I will do it after. Okay, and but this and so we want to we want to take the L2 completion of this thing. So now I will say I will do this thing, and I will ask that this is not finite anymore. But then I will ask that the sum of lambda. Okay, but now I have cheated just a bit. And we know, yeah, just what I wanted to say is that here, this point here, I blow up points, but it's like before. I don't just blow up the point of P2. So I blow up all the point of P2, but also the points which appear in the exceptional divisor and so on. Okay. And I wanted to just make you see that I cheated a bit here, because I said, I take a line which is not passing through P. Okay. So what will happen if I would have taken a line that will pass through P? So now if I will blow up the point R here, then I will get my ER. Let's say that I did this instead of taking this one. I don't take this point. So this now I have -1, I have -1, but now the line is of self-intersection 0. So this is a bit problematic. I don't have this nice thing anymore. But this is because, in fact, you have to pay attention. You don't really take, so this thing is what is called the strict transform of the line. So it's just that, so this is, so L bar, this is the strict transform of L. So in fact, you take the closure of the blow up minus, so you take, so this is the map pi R. So you take the closure of pi R of L minus the point you have blown up. Okay, so this gives you just this thing. But in fact, if we want that the intersection form doesn't depend of where you took the point, you have to take the total transform. So in fact, you don't want this thing. You want to take the total transform, meaning exactly all you get if you take the inverse of L. So all you get above L is this thing plus this thing, right? And now if you look at the self-intersection, so you take let's say L plus ER, and now you self-intersect it. So this is a divisor, and so this gets, so the strict transform squared is 0. This times this is 1. This times this is 1, so 2, and this is -1. So we get 1. So to be well defined, we don't have to just take the strict transform that we would like to take, but really all of what you get above. So just here, it should be some small to say that you want the strict transform. In fact, if you do this, it means that it doesn't matter on which model you are. Okay, so anytime you will want to compute something, in fact, you will not go so far. You will just go to the stage where you can see everything. And in fact, if you will have known a few more points, you don't want that it change this intersection thing. Okay. And okay, and you have to, okay, now you do this. And if you take a surface, you blow up a point P or a point Q, then you can blow up the 2 points, so you can get a surface above, where if you intersect a divisor which comes from here and a divisor will come from here, in fact, you switch here and you intersect it here. So this is just to say that you can really well define the intersection form. Okay, because you could take a divisor. In fact, this tells you that the inductive limit is well defined. Okay, and so now we have our H infinity inside this thing, which will be like the class belonging to the Pickermann space that are of self-intersection 1, and such that C times the class of the line is positive. And this gives you exactly the H2 I spoke to you about before. But now you see that you have all the points blown up plus the line give you the basis, which is uncountable if your field is uncountable. Okay, and okay, you have the classical, so distance between two classes is the R cos H of the intersection number. Okay, so now we will see how the group, how Cremona group act on it. Oh, well, but before, do you have a question about this thing? No, it's okay.
Can you give what examples of divisors that lie on this?
Sorry?
Can you give examples of divisors that lie on this hyperbolic plane? So the original line lies.
Yeah, so for instance, if you, yeah, the line, so the, okay, so in fact, you will have something like, So a base will be the line. Then you take a point that you have blown up. You have the class of the exceptional divisor, and this will give you all the things like this. So of course the line is inside, but if you take twice the times of the line and you blow up 3 points, this also of self-intersection 1, and you can do okay. And now I give integer, but you can do it with R. But this is nice because well, this one is the one we will see just now. Oh, no. So, how do we make the Cremona group act on it? So, in fact, we will just see, well, in fact, we will see. I'm really sorry with the. In fact, we will make act the Cremona group on this one, and then okay, you have to check that it's well, that it preserves the element of self-intersection 1.
You say the Z bar P2, the countable research. Could you explain what that's basically adding is?
Yeah, so this is the indicator. So in fact, so each time you blow up point, you have new divisors that you can add in your basis, and you do this at infinity. So you blow up all the points you want, but you have this means that you want to identify points. Okay, so for instance, okay, what does it mean? That if you're on P2 and you have the line, this is the same point as if you blow up a point and you have the exceptional divisor of the point. So this space means that you want to identify things that are the same. So you don't want to say that this divisor is different than this one. They are the same. So this is a way to, and the basis. So the basis of this thing is the class of the line and all the points you can blow up. So all the exceptional divisors appearing in points you blown up, and this gives you all your basis. Okay, and the point that we take the completion like this, we have something which is complete. So you have to add this condition on the coefficient. And just so we will make the Cremona group act on it, and just to understand what is happening. So here I said that it's the space associated to P2, but because we take the inductive limit, if we have so if you blown up a point in P2, you have a surface above, and we have said before that the Néron-Severi group of this one was generated by the line, and now this is generated by the line and EP. Okay, so in fact, when you do something like this, so when you just blow some points, what you do in this space is just that. So this is kind of the exceptional part. So the self-intersection is -1. So this is the exceptional part. And what you do is that when you go on surface above, just some of the points, they belong to your they are real divisor in your surface anymore. So it's just a switch of which one is called exceptional and which one is really in your surface. Because if you're in P2, these guys, you don't see them, they're points. You don't, or even not points, they are, you don't see them. But then when you blow up, you kind of start to see them really as a curve, well, a real curve in your surface. And this switch on this way. Okay. So just to say that if you have a morphism between the surface and P2, the Picard-Manin space associated are isomorphic. It's just a matter of what is exceptional or not. So now we are ready for. So it goes from P2 to P2, and we know that there is a Zariski minimal resolution. So you have W. This is a composition of blow-up, and this is composition of blow-up. So here we have the Zariski space of P2, and we do something, and we are to the Zariski space of W that are isomorphic. But just here we have decided which one belongs to the space and which one no, which are determined by the point you have blown up here. And on the other side, we have the same. And the action is just how F send curve to curves and how you write them in one basis to the other basis. So, okay, so in fact, so the action of, so let's see belonging to this. So the formal definition of the action is that so you do the action on the curve by this one, and you go down. But okay, this I think it doesn't really help. So maybe we do just the example of the quadratic standard to understand how we deal with it. Okay. No, I'm sorry. This quadratic involution, which was sending xy to 1 over x, 1 over y, and we had this so sigma. No, so I will do it bigger. And is it bigger here? Or can you see? And we said that if we blow up the 3 points of coordinates, so here you can do in the order you want. So you blow up these 3 points. So I did the picture 2 days ago. Now you get an hexagon. So you have the blue line, red line, and the green one. And you have this one. Can I get it? Yeah, okay. Well, you have these 3 lines which correspond to this one. And then these are contracted to this one, and this one. So now we want to understand, so it is enough to understand the action of F on the basis, right? So maybe we should start with a point P, and if P is not a base point of F, if we take a point P where F is a local isomorphism around, so it means that P is not a base point, but also P doesn't belong to a curve which is contracted. Okay, so if P doesn't belong to these 3 lines, okay, if it's in P2, then the image is on someone elsewhere. So then the image is just okay, and if it's above a point like this, okay, you have also you have a local isomorphism. So now the things which is more complicated is to understand how the line is sent, all the 3 base points are sent, and all the line of coordinates are sent. Okay, so let's start with the line. So I take a line in P2, okay, and I can move it around, somewhere else from the 3 points. Okay. Now my map, okay, it's not written like this, but it's a quadratic transformation. It's a quadratic map. Okay, so it's of degree 2, so it has to be a conic here. Okay, and okay, if you look a bit the equation, it has to be a conic passing through the 3 base points of the inverse. So it's a conic that passes through this point, and this point. Okay, and now we want to understand above what happens. So this was my line. So okay, it's supposed to cross. So I don't know what to do, but something like this. Okay, so now we have the class of the line. So this is my real line. And I said that we want to look at the total transform. Okay, here we didn't blow up point on this line. So the total transform here is still this is also the total transform. So this is what I call the total transform, okay? This is exactly what we see. But now from this side, the yellow curve, which is a strict transform, is not the total transform. Okay, so the yellow curve. So let's say the total transform is the yellow curve plus the 3 exceptional divisor of the inverse. Okay, plus this. So we have blown up this point, we have blown up this point, and this point, so that correspond to these 3 lines. Okay, plus so I will call them. I will call this point. Okay, I call it P, Q, and R. And you have somewhere blue and red. So you have EP, or ER, and EQ. Okay, and so the yellow line is sent to this yellow curve. And so now what I say is that this guy, it corresponds exactly to just the yellow one. So in terms of divisor, the action on the line, F of L, it will be in this side exactly this L bar, which corresponds exactly to this C bar. Okay, but this is not in terms of total transform. Okay, and this is exactly this minus this minus this minus this. So this is the strict transform of C, the total transform of C minus EP minus EQ minus ER. But in terms of divisor, this is just now a random conic, and this is twice the line. So this is 2L minus EP. Okay, so this is my action. And in fact, if you take any birational transformation and you make it act on the line, you will get, in front of L, you will get the degree of the application F. And here you will get the divisor associated to the base point of the inverse. So you get the base point of the inverse. Okay, and here you have multiplicity 1, but you could have, well, you have the multiplicity of the base point that I didn't introduce. But so in fact, acting your application on the line, you get really a lot of information of your element. Okay, and just for instance, if you want to understand what is so here you have the point P. If you want to understand the action of L on this point P, okay, now you are here, and this line, it was corresponding to this line, and doing the same trick, you will see that this corresponds to the class of the line minus EQ minus ER. And okay, so this will give you the things for these 3 points. And now if you take a point here that is contracted, so this line is contracted. So here you go to a point here. But so this will be a point M on your exceptional divisor. And now from here to here, it's a local isomorphism. So you will send the class of this point to the class of. Okay, so this is how it works. And okay, it's nice to have H infinity. Well, H infinity is also Gromov hyperbolic, is also cat 0 because every condition is on triangle, so it's stay on the plane. And maybe in the 1 minute left that I have, I will state a nice thing is that you have a nice classification of isometry for group acting on hyperbolic space. So
Just can you move up to the board on the bottom right?
sorry,
You just move up to the board on the bottom right.
this one.
Yeah.
Ah, sorry, down. Sorry. Okay, and okay, and just so here I said that the degree. So the action is the arc hash of the intersection number. So if I intersect this with a line, okay, this will give you the degree of F, and because I have a basis L against EP or against EQ or against ER is 0. So each time I intersect this against the line, I will get the degree of my map. Okay, and so the distance is really well related to the degree, and we have a theorem. So if you have a birational transformation, we have this theorem saying that if you look at the sequence of degree of Fn, okay, then this sequence is either bounded, so either linear, quadratic, or exponential. So this is due to Dillard-Favre and Gizatulin. And what is nice is that we have really a classification that corresponds to the action on the end of the hyperbolic space. So this one will be, so this was a remark done by Kanta. So this will be exactly the one which are elliptic for the action on the H infinity. These two will be exactly the parabolic one. And in fact, these two maps, they preserve a fibration that will be encoded in the fixed point at infinity. So the fixed point at infinity, there will be of this form, or so this a pencil of line, or a pencil of a conic passing through 9 points. And if it's exponential, this will be logarithmic. And okay, I will stop here. Thanks.
Questions for
How do you define the degree of the last map?
Sorry?
How do you define the degree?
This was the degree of the polynomial. So F is given by 3 homogeneous polynomial of same degree without common factor, and this is the degree of my map. So the degree, you never find it in local. So here you never find the degree like this. You have to projectivize and look at the degree of the polynomials.
Just wondering, the action of the Cremona group on this space won't be acylindrical necessarily, right? But
No.
We're going to produce an WPDL.
Yeah, but the action will be not acylindrical on this space.
Okay.
Yeah, in fact, you will have you will have this GL to Z that I introduced. But maybe I will tell a bit more, but then they will not act loxodromy on. Sorry, it will be loxodromic elements that are not at WPD.
Okay.
So you have trouble here. Yeah. And just.
More questions. There is a second exercise sheet. Yeah, I had last question. So you talked about boundary points of the space.
Yeah.
I did not quite get what they look like.
So there will be, there will be exactly so. So in fact, it's like in the H2 case. If you like the hyperbolic model, the one it will be the one of where the billion form gets to 0, and this will be exactly the class that the self-intersection is 0. So if you look at this guy, for instance, this is L to the square x 1 minus 1 is 0, and you can do this. So there will be the class of self-intersection 0. And the orbit of the point on these things, there will be the one, well, not all, but in fact, when you act here, you see that it's then you get integer here. You don't get something else, but your ambient space is in C.
So
in R. Sorry.
You showed at some point something that was of self-intersection 0, but in the examples.
So sorry? Yeah.
So that was a boundary point.
No, so this was the yeah, so this is not a bond. So this was the curve is of self-intersection 0, but it's not a total divisor. And here I want the total divisor. So this was not. Okay. But if you do this thing, in fact, if you do L minus EP, you want to take, so if you take this divisor minus this one, then this will be a boundary point. It's a formal sum, so it's not it doesn't have a geometric meaning.
Yeah. Other questions? If no, we have done today and resume tomorrow at don't remember with
9:30.
9:30.